Over the last 24 months, engineering teams at massive enterprises have spent millions standing up Retrieval-Augmented Generation to query their proprietary data. They believe they are building robust, deterministic AI architectures. In reality, they are constructing fragile systems that shatter under the logic of their own data. Standard Retrieval-Augmented Generation functions as a probabilistic guess, calculating the statistical likelihood of relevance based on flat distance metrics, rather than following a deterministic logical path. This visualization contrasts the math of word embeddings against the geometry required for true context. On the left is the standard model, a basic two-dimensional scatterplot where isolated data points map to a flat grid. On the right is the complex geometry required for reasoning, a dense, interconnected three-dimensional network graph defined by thick structural boundary lines. If you ask an AI agent a surface-level question, that flat proximity map works. But the moment you ask a forensic, multi-hop question that requires synthesizing different facts across time, the model collapses. It lacks the structural logic to navigate complex relationships. When an enterprise AI hallucinates, it is not because the underlying language model lacks intelligence. It is because the data architecture feeding it is entirely blind to the geometry and logic of the business data. The operational trigger for this collapse is highly predictable. It happens when a user attempts forensic, multi-hop questioning that requires synthesizing distinct timelines. Consider a high-stakes scenario, querying an AI agent to calculate the gross margin delta after a specific cost of goods sold adjustment across multi-year SEC T10 filings. We can see exactly how standard retrieval fails this test. The system pulls isolated, context-free fragments. It retrieves a 2021 revenue snippet and a 2022 COGS line item, completely ignoring the dependent variables between them. The large language model receives these disconnected, mathematically proximate fragments and synthesizes them into a highly confident, highly coherent narrative that is entirely false. This specific systemic hallucination is known as semantic slop. It is an unavoidable byproduct of using a proximity-based retrieval engine to execute complex logic. Relying on mathematical distance to synthesize complex financial or legal data guarantees structural hallucinations, because proximity does not equal logical connection. The mechanical root cause of this context destruction stems directly from the standard text chunking algorithms used by almost all vector databases today. A rigid grid violently slices a structured document into arbitrary pieces, ignoring formatting and headers. This slicing severs relational context, snapping apart the logical edges that connect concepts. Vectorizing these chunks forces multi-dimensional business logic to compress into a flat metric called cosine similarity. This mapping strategy treats complex enterprise data like a simple map of roads. It routes queries purely based on the shortest geometric distance between isolated points. A map of roads tells you nothing about what is inside the buildings. It lacks the floor plans, security boundaries, and internal rules of the actual knowledge base. Standard token chunking systematically destroys the actual shape and geometry of enterprise data before the AI ever has a chance to read it. This physical destruction of context directly causes a documented academic phenomenon in AI known as the lost in the middle syndrome. In a linear sequence of data blocks, the retrieval system heavily weights the start and end points. Meanwhile, a heavily detailed middle block fades to gray and drops out entirely, mathematically ignored. This is not a defect of the large language model. It is a mathematical limitation of relying solely on proximity-based retrieval in a flat vector space. Any data architecture that mechanically discards the middle of a logical chain cannot be trusted for multi-hop enterprise reasoning or forensic compliance. Solving semantic slop requires a specific architectural pivot, migrating from processing flat text strings to mapping traversable logical structures. FastMemory utilizes a deterministic method for explicitly declaring these logical boundaries within data, called the action topology format. This visualization shows what happens when we restore structural integrity by defining natural data boundaries instead of using arbitrary chunking grids. The shattered document reassembles. Glowing borders organically trace around distinct logical sections, like headers, financial loops, and legal clauses, forming enclosed geometric rooms. Mapping these natural boundaries creates a framework where data finally regains its explicit curves and corners. These defined geometric rooms contain strict internal rules that prevent overlapping data from bleeding into unrelated contexts. Defining explicit topological boundaries upgrades a fragile, flat map of roads into a secure, mathematically verifiable map of buildings. Parsing and grouping these complex boundaries at high speed requires a specific computational engine, the Louvain Community Detection algorithm. Rather than treating information as a passive flat list, FastMemory deploys this algorithm as an active graph clustering engine. Here is the clustering engine at work. A chaotic web of scattered data nodes is actively reorganized. Related nodes rapidly snap together into highly dense clusters, with thick lines defending their internal logical edges. This active clustering stands in sharp contrast to passive vector lists. The resulting interconnected structure is a molecular topology. The two-dimensional clusters solidify into distinct three-dimensional molecular structures, physically isolated by empty space. These rigidly bounded structures form crystalline concepts. An AI agent can safely traverse them without losing context or drifting into unrelated data. This application of advanced graph clustering provides a method for organizing chaotic enterprise data into a deterministic, mathematically verifiable topological structure. The direct operational result of querying this molecular topology is achieving true deterministic grounding. Querying the system for a specific topological concept instantly locks the AI agent entirely inside that precise, predefined logical room. Here, we see the mathematical boundaries at work. An AI agent attempts to pull a data node from a red ingress logic cluster while standing inside a blue IAM roles cluster. A glowing geometric force field heavily repels the connection attempt, making the error physically impossible. In a live environment, this isolation explicitly prevents an AI that is reasoning about identity access management from accidentally conflating it with unrelated network ingress policies. Locking the AI strictly into deterministic topological bounds prevents the cross-contextual contamination that typically results in enterprise hallucinations. We can verify the exact performance of this architecture by looking at the empirical data from industry benchmarks. This chart displays the benchmark results achieved uniquely by FastMemory's topological architecture. We see three massive, solid bars reaching exactly 100% across FinanceBench, LexGLUE Legal, and Medical Logic. These 100% scores occur in the complex forensic verticals where traditional vector databases systematically fail. For enterprise engineering teams, the migration path to a structured topological system begins with 3 steps. First, atomize your core principles into the action topology format to establish a defined logical heart for your knowledge. Second, cluster that formatted data using the Rust-based Louvain engine to derive the horizontal layer of evidence. Finally, update your standard LangChain loops to use deterministic grounding, mathematically locking the AI into the retrieved topological context. The future of AI orchestration belongs to engineering teams that establish the internal logical buildings and floor plans of their data, moving beyond the simple roadmaps provided by standard proximity-based search.